is something like this. You have an hydrograph, QT depending on T, river discharge depending on time, and you have an observed hydrograph. Let me see if, no, there are no different colors. You have an observed hydrograph like this one, and this is observed. And then you try to calibrate, meaning that you try to interpolate with the model this hydrograph. And typically you may get a result like this, which is not bad. Of course, the simulated hydrograph is not perfectly matching the observed one, but this is quite close. And this is interpolation, meaning that you find a mathematical relationship, the dotted line, expressed by the dotted line, that is interpolating your data. But in order to generate synthetic series, you need to extrapolate this. By using, for instance, rainfall data. Rainfall data that you have observed for a period which you didn't observe the river discharge data. So you are extrapolating the parameter values that you calibrated in a period for which observations were fully available, you are extrapolating, okay? And if you have two parameter vectors that give to you similar performances in interpolation, they may provide very different hydrographs in extrapolation, because extrapolation is something much different. So if you have, again, different parameter vectors that give the same hydrograph here, when you use the model to simulate an out-of-sample situation, out-of-calibration sample situation, you may get different hydrographs. And therefore, of course, you are interested in getting the parameter vector that gives to you the most reliable simulation. And you don't have any element basing only on calibration to understand. You have to make additional analysis, like including more information. Therefore, the suggestion is need to use all the available information. And this is a broad suggestion, meaning that even when you identify the model, you decide which model to use, you have to decide to use a model that allows you to take advantage from all the available information. Again, you must select the model that allows you to use all the available information. Therefore, if you have, for instance, soil moisture data available, you have to use a model that allows you to check if soil moisture is well reproduced. This is the suggestion. Don't be much concerned, because I am aware that understanding these considerations without trying, it's not easy. But actually, when you go to professional design, there are a few rainfall runoff models that are used, which are quite easy to understand. And therefore, it's quite an immediate consideration to select the model that is most appropriate depending on the level of information that you have. Second issue, you can use multi-objective calibration. You can use more than one objective function, because two different parameter vectors may give to you similar value for one objective function, different values for another objective function. So the suggestion is try to use, if you are in doubt, multi-objective calibration. How to combine two different objective functions? How can I use more than one objective function? There is a trivial suggestion, which is use one, and if you are in doubt for among 3 or 4 parameter vectors, several parameter vectors, just compute for each of the alternative possibilities a second objective function. and see how they behave with respect to the second objective function. This is a trivial suggestion. Like, I am using least squares. I see that theta equal 1 and theta equal 5 give to me similar values for the sum of squares. Then let's compute the mean relative error for these two parameter values, and let's see which one performs better. This is the first trivial suggestion. The second suggestion is to compute an objective function which is the combination of two or more ones. Like, we can compute an objective function f theta, which is given by w1 ls theta, where ls is sum of squares, plus w2, which multiplies mean absolute relative error of theta, where w1 and w2 are weights that give more or less emphasis to each one of the two objective functions. And of course, here there is a problem that the order of magnitude of the two objective functions can be different, because the sum of squares can be very relevant, very high, while the mean absolute relative error varies varies between 0 and in principle 0 and infinity, in practice 0, 1. Okay, and therefore you see that we have to assign an appropriate weight depending on the order of magnitude of the objective function, and also the weight that we want to give to each one. Basically, when we combine objective functions, it's better to combine together objective functions that vary in the same range. Like, for instance, Nash-Sutcliffe efficiency, which varies, as I said, between minus infinity and 1, but basically it's 0 and 1, and the mean relative error, which varies between, again, 0 and 1. You have also to be careful because for the Nash-Sutcliffe efficiency, optimal values correspond to 1. For the mean absolute relative error, optimal values correspond to 0. So when you combine, you also have to be careful, because you have to decide whether you want to maximize or minimize the result. To decide the value of the weight is a subjective procedure for which rigorous approaches have been suggested, which we are not taking into account, we are not dealing with. We just want to mention that this is a possibility. There is also a more rigorous approach to combine two objective functions. And let me try to provide an example. Like, let's suppose that we take as objective functions least squares and mean absolute relative error. And a possibility to select the parameter vectors that are best with respect to these two objective functions. A possibility is to draw a graph which displays one of the two objective functions on the abscissa, and the other one And therefore, once that you pick up a parameter vector by chance, you can put a point in this plane. Like this is theta 1. Theta 1 corresponds to a given value of the mean absolute relative error and a given value of the sum of squares. Keep in mind that for both these objective functions, our purpose is to minimize them. For both the mean absolute relative error and the sum of squares, our objective is to minimize them. Okay? Now, let's try with another parameter value, and let's suppose that this parameter value is theta 2, and we can put it here. Now, of course, if we compare the result for these two parameter values, we would say that theta 2 is better than theta 1 because it's characterized by a lower value of the mean absolute relative error and the sum of squares. So we don't need to keep in memory theta 1 anymore. Now let's go on with another trial value like theta 3. Let's suppose that it's here. Now, in this case, we have an higher value of the mean absolute relative error for theta 3 with respect to theta 2, but a lower value of the sum of squares. So, theta 3 is better than theta 2 from the point of view of sum of squares, but it's worse from the point of view of the mean relative error. So we cannot decide which one is better. Let's keep in memory them both. Now, let's suppose that we now select by chance another parameter vector, theta 4, which is placed here. In this case, theta 4 is better than theta 2 and theta 3 for both objective functions, so we can keep just theta 4. If we move forward and proceed accordingly to this algorithm here, so we forget about the parameter vectors that are dominated by another one, where dominated means that they have worse performances for both the objective functions, and we keep in memory only the parameter vectors that are not dominated, then we typically obtain a curve like this. And we may have here different parameter vectors, theta 1, theta 2 prime, etc. And typically it's a curve that has this kind of shape because you know, there is a region where we can find only dominated solutions, but if we look at the non-dominated solution, where non-dominated means that each one of these solutions has a value of at least one objective function that is the best one. Okay, or let's say it was not correct, sorry, I didn't translate correctly. Let's say that this solution are non-dominated, meaning that you can't find a single value of the parameter vector that has both objective functions that are better of the considered one. So for this solution here, theta 4, I say that it's non-dominated because I cannot find another parameter vector that has both the objective function that are better. Okay? And therefore, you typically end up with a curve that is displaced in this way. Of course, you may have different shapes, but typically it's this shape here. This is called the Pareto frontier, in Italian frontiera di Pareto, meaning that it's the curve where non-dominated solutions lie, and they constitute a frontier for all the possible parameter vectors. Now, for each one of the points that lie on this curve, for each one of them, you have to spend some thought, because of course you can identify two parameter vectors that correspond to the best one objective function, like the limit of the frontier are these two parameter vectors, for which in this one, let's call it theta star, and this theta double star. So theta star corresponds to the best possible value for the mean absolute relative error, and theta double star corresponds to the best possible value for the sum of squares. So you have these two options which are relevant because they correspond to the best value for one objective function. But of course you don't have any criteria available to select between these two possibilities, and also all the other possibility lying on the Pareto frontier. Each one of them represent a potentially interesting combination. So the moral of the story is that this approach allowed you to reduce from a very large amount of points to only the parameter vectors lying on the Pareto frontier. And therefore, on this limited number of parameter vectors, you have to concentrate your attention and basically try to make a choice based on, for instance, alternative information. This is called multi-objective calibration. Usually, when you talk about multi-objective calibration, you refer to solutions that are searched through the identification of the Pareto frontier. We may say that you can call also multi-objective calibration the procedure in which you combine the two objective functions instead of looking at the Pareto frontier. But classically, when you talk about, especially in English, multi-objective calibration, people understand that you are referring to identifying the Pareto frontier and identifying several alternatives lying on the Pareto frontier. But especially in Italian, you can say calibrazione multi-obiettivo even when you combine the objective function without passing from this Pareto frontier. Keep in mind that you can use an unlimited number of objective function, and you will end up with, in any case, with the Pareto frontier, which is a hyperdimensional surface if you have many different objective functions. Let me look at the next one. Okay. Now let's to move another step, and let's refer more specifically to the issue of checking the model performances, and therefore checking what is the best parameter vector with respect to extrapolation. I mentioned before that you have equifinality, and you have to be concerned about equifinality, especially because the parameter vectors can be equifinal in calibration, but not in extrapolation, not when you turn to using the model. Therefore, you can understand that a critical issue is to try to check the model. Once that you calibrated the model, a critical issue is to try to check it by referring to real-world application, to the real use that you want to make for the model. In our case, we want to use the model to generate synthetic data. This synthetic data must be representative of the real world. Therefore, one important issue is once we calibrated the model, in view of the problems that I outlined before, equifinality, overfitting, so we are aware that there are potential problems, so a critical issue is to try to check how the model performs in application. How the model performs when I use it for the purpose for which the model was identified and calibrated. And this procedure to check model performances in extrapolation in a real-world application is also called validation or verification. I prefer the use of the term validation because it's much more similar to the Italian term validazione, and in the international literature it's less clear what validation means. But in any case, you can use it also in the international literature. If you Google validation and hydrology, you find a lot of entries. So what is validation? Validation is, again, subsequent to calibration. So you already have your model with your parameter vector, and you try to understand how the model performs in a real-world application. It's a check before application. Now, how can we carry out validation? You already understood that in order to carry out validation, we have to emulate a real-world application. We have to pretend means that facciamo finta, to use the model in the real world. And therefore, this is called also extrapolation, as you understood by my preamble. Or it's also called out-of-sample application. Out-of-sample means implicitly out of calibration sample. The sample of data is a set of data that is implicitly refers to the data that we used in calibration. Now, when we say out of sample, it means that we use the model by referring to data that we didn't use in calibration. And there are different alternatives for doing so. The first obvious alternative is what is called split sample calibration and validation. Split sample. Split sample means that you get a sample of data and you split them into parts. The first part is used for calibration. The second part can be used to check how the model works in the real world. Let me try to be more explicit. Let's suppose that you have an hydrograph that you can use to calibrate the model. Q, T, as a function of T. And let's suppose that you have an hydrograph like so, which is long for an assigned observation period. And therefore, what you can do, instead of using all this data to calibrate the model, you can just pretend that your sample ends here. Okay? You cut the sample here, you split the sample here, and then you can pretend that the second part doesn't exist, and you calibrate the model, therefore fitting the first part of the sample. And let's suppose that you get this dotted line until here. Okay, so you interpolate this data with calibration until here. Now, at this stage here, you have identified a parameter vector. For the second part, you have the rainfall data, you have the parameter vector, you can run the model. independently of the fact that you have observed data. Let's forget about the observed hydrograph. It doesn't exist. Okay? So basically what I do is I run the model and I extrapolate. I work out of sample, and let's suppose that I get a situation like this. At the end of the story, I remember that I have the observed data, and then I can plot together simulated data and observed data that I did not use in validation, in calibration, sorry. And therefore this is a comparison that is meaningful of model performances in real world. Because in the real world I don't have the observed data, because if I had them, I wouldn't need the model. But it's a similar situation with respect to this one, where I pretended that I didn't have the observed data. And typically, as you can understand, you get a worsening of the performances in the second part. Because for the first part in calibration, the model was forced to fit the data. In the second part, the model is not forced to fit the data. It was forced just to fit the first part. In the second part, he is working out of sample. He is extrapolating. So, of course, you can imagine that the performances in the second part must decrease. Should decrease, not must, because if you are lucky, of course, if you are lucky, you can get a second part of the hydrograph, which is particularly easy. Model performances could even improve. But usually when I get better performances in validation with respect to calibration, I get suspicious. I think maybe I made something wrong, because it's very, very unusual. Usually what you have to expect is a worsening of the performances. Anyway, this is called split sample validation, which means that you get your data, you split the sample, use the first part for calibration again, and then the second part for verification or validation. There is a problem in doing so, that, as I said before, we have the problem that we don't have many data, and therefore we are forced to use all the information available. I told you, try to use all the information available in calibration. While if you use the split sample technique, you are not using in calibration all the information available, because you are reserving a part of the information for validation. So, split sample validation is criticized by some researchers who say that it is not efficient. So, what is the final suggestion? I hope to be able to deliver the concept in an easy way, because it's a very simple concept. What is the final recommendation is you have to check your model performances with a kind of validation. If you decide to use the split sample, because it's the type of validation that is easier and also more representative, there is nothing wrong. Just split the sample and make this comparison. But at the end of the story, when you have checked that your model works quite well, then recalibrate the model by using the whole hydrograph. Because when you go to using a model, indeed, the suggestion is calibrate the parameters with the higher number of observations, the highest possible number. So there is nothing wrong if you split the sample first, you check the model performances, but before applying the model, finally you recalibrate it. There is one thing, one observation that you may formulate, which is if I do like so, the model that is validated, the parameter set that I validated, is not the parameter set that I'm finally using, because I recalibrated the model. Okay, I hope you understand what's the problem. If you validate the model and then you recalibrate the parameter vector, because you want to use all the information, it means that the parameter vector that you validated is not the one that you are finally using. That's good, but I think it's the best solution, the best possible solution, a pragmatic solution. What else should we do? If we want to perform both validation and model application with the maximum amount of information. What else can we do? So you see that the procedure is a bit complicated. You have to get your data, to split the sample, calibrate the model, check it, and then recalibrate the model, and finally apply it. The procedure is a bit complicated. There is an alternative to the split sample calibration, which is jackknife validation, and it's an alternative that is increasingly used. It has the problem of being computer intensive, and I'm trying to explain. The idea is the following. Let's refer once again to split sample validation. And we decided to keep the first part of the hydrograph for calibration and the second part for validation. And then at the end we recalibrate everything, okay? There would be a second solution, to use the second part of the hydrograph for calibration and the first part for validation. So, in general, we could use this procedure. Let's suppose that we have 10 years of data. We can use 9 years for calibration and 1 year for validation. And we can perform all the possible alternatives, meaning that I can keep the first year for validation and years from 2 to 10 for calibration, or I can get the second year for validation and years 1 and 3 to 10 for calibration, and I can change the validation period along the hydrograph. The validation period should be kept long enough, so I would say at least 1 year. If you want to perform generation of synthetic data, I think the validation period should be at least 1 year, because if you generate just one data point, it's not really a long enough validation. But once that you get a sufficiently long period for validation, you can move this validation period inside the hydrograph by repeatedly performing validation. This means that you are minimizing the amount of data that you reserve for validation, because you don't need a very long period. You need a period that is long enough, like 1 year, but because you change this 1 year period, at the end you obtain a validation that is 10 years long. So it's long enough. So you can minimize the length of the validation period, and this is of course good. And also you get a validation for a very long period, the whole hydrograph. So this is really very efficient. The only problem is the computational requirements and the fact that the procedure is complicated. Because you have to continuously change the validation period, recalibrate the parameters, etc. But this jackknife validation, which is also called leave one out, this is a synonymous, is also called leave one out. This procedure, this leave one out procedure, it's synonymous of jackknife. Leave one out, why? Because in this case, you leave out 1 year at each time. So leave one out. I said if you have 10 years of data, you can exclude 1 year for validation and then change the position of the validation year. So it's a leave one out. Leave 1 year out in this case. I think, okay. Now let's turn to a easier conversation. With a final, I'm closing now the issue of automatic calibration and and calibration validation, let me make a final recommendation. Always look at the hydrograph. Don't look just at the value of the objective function. When you get a response from your computed code and you get a parameter vector, an optimal parameter vector, don't just look at the objective function and parameter values. Don't just look at numbers. Look at reality. Reality is the hydrograph. So let's look at the comparison between observed and simulated hydrographs. Because you will see that some simulations are characterized by very good objective function values, but they are not good from a physical point of view. Because sometimes something strange happens. Maybe that you have a very good objective function because you got very good peaks. So if you're using least squares, if you get the peaks, you have a very good value of the objective function, but you may see that the droughts are very poorly reproduced. And therefore you may decide to reject this solution because it's not reasonable. So always look at the hydrograph, even when you use automatic calibration. We will see that it's also possible, while the PC is performing the automatic calibration, to tell the PC to plot each time the resulting hydrograph. So you may even do so. To tell the PC each time that you try a parameter vector, please show me the hydrograph. This is a good solution if you really want to check what's going on. Of course, it's time-taking because, you know, if 10,000 computations are requirements, you can't look at 10,000 hydrographs. Now, let me go back to the manual calibration. For the manual calibration, as I said, you don't need to set up an objective